My name is Yifei. I recently graduated from Stony Brook University and now a software engineer at Google. I'm going to talk about our work, enhanced file system testing through input and output coverage. This is joint work with Stony Brook University and Harvard College. File system bugs are serious, and even with extensive testing, they still emerge, even in well-tested file systems. Coverage is important because to expose bugs, we need to test a wide range of corner cases. Therefore, testing tools rely on coverage metrics to guide testing. The most common one is code coverage. These metrics help us evaluate how well tests cover the system and provide feedback to improve them. Ideally, effective metrics mean more coverage can lead to more bugs being found. Code coverage measures how much of the source code under test is actually exercised by the testing tool. It can be measured at different levels, such as lines, functions, branches. This measurement provides insights into untested part of code, helping us improve our tests. Code coverage has limitations in file system testing. First, the mapping between the test inputs and code is not clear, making it difficult to increase coverage by adjusting inputs. Second, collecting coverage data requires a substantial effort to instrument kernel code. More importantly, no previous research has examined the correlation between code coverage and test effectiveness in file system testing. To study whether code coverage reflects the test effectiveness, we analyzed 70 recently reported bugs from ESD4 and BTRFS. We ran XF tests to see if it could detect these bugs. At the same time, we record its code coverage from these file systems. We found that XF test meets all the bugs, even though it can achieve line coverage, function, and branch coverage on many of them. Further, we observed that most bugs require specific syscall arguments to trigger, and many occur on exit paths that affect syscall return behavior. We call this input and output bugs, respectively. This highlights the importance of covering diverse syscall inputs and outputs in file system testing. There are two key takeaways. First, code coverage is not strongly correlated with test effectiveness in file system testing. Second, covering both syscall inputs and outputs is essential for thorough file system testing. Understanding what inputs and outputs need to be covered is crucial. But syscall space is very huge, so we narrow down our focus to file system syscalls only, out of about 400 Linux syscalls. Even then, the space is still very huge, still large, because syscall accept arbitrary values as inputs and can return many different returns, such as different error codes. To address this, we partition the input space by collecting similar arguments. We classified argument into 5 categories: identifiers, pointers, bit masks, numeric values, and categorical values, and then applied partitioning rules that are specific to each different category. For outputs, we partitioned by success or failure, by error codes, and by powers of 2 for return values in bytes. Using these partitions, we define input and output coverage as the extent to which a file system testing tool exercises input or output partitions. We implemented a framework called IOCOV to make it easy to compute input-output coverage for file system testing tools. We use LTTNG as the syscall tracer to capture inputs and outputs. The collected syscalls are then passed to the IOCOV analyzer. The analyzer first filters traces to retain the traces syscalls only related to file system testing. It also includes a syscall variant handler to merge coverage across variants, such as open, create, open add. They all represent open operation. Finally, with these selected traces, the partitioner divide the input and output space, and we compute the input and output coverage based on the partition results. The purpose of I/O curve is to evaluate input and output coverage and improve testing tools. And ultimately, we want to help to find more bugs. As an example, we applied it to Crash Monkey, a tool for testing file system crash consistency. Crash Monkey simulates crash by replaying I/O and then comparing file system state after the crash to an oracle. And if there is discrepancy, it flags it as a crash consistency bug. With I/O curve, we extended Crash Monkey into CM I/O curve, enhancing its input coverage with the goal of uncovering more crash consistency bugs. Specifically, Crash Monkey's test workload were based on fixed and chosen inputs. We replace this with a new CML curve input driver that generates workloads covering more input partitions than the original Crash Monkey. With this driver, we support a much wider range of inputs. For example, we can now handle more open flags, additional file directory modes, and broader byte values for let's say operations such as write, L6 offset, allocate. Altogether, this results in specific, very significantly better input coverage. We use CML curve input driver seamlessly for input generation while reusing all other parts of Crash Monkey. In this way, we focus the improvement only on the input coverage and clearly see its impact on detecting crash consistency bugs. Now, let's look at the evaluation. I/O curve currently supports measuring input-output coverage for 27 file system syscalls, including 11 base system calls like open, read, write. We applied I/O curve to 4 different testing tools: Crash Monkey, XFI test, Syscaller, Metis, on the same ESP4 file system. These 4 tools represent 4 different approaches, like automatic test generation, regression testing, fuzzing, and model checking. To ensure fairness, we measure their input and output coverage under the same amount of testing time. Here, we present input coverage results for 4 testing tools, which focus on open flags. On the x-axis, we show the individual open flags that are input partitions for this syscall argument. On the y-axis, we plot the frequency of each flag on a log-based 10 scale, showing how often each open flag is exercised by the testing tool. Let's look at 2 flags, like async and large file. We found that only Syscaller exercises these flags, while other 3 tools completely miss them. At the same time, some other flags were exercised by millions of times. This illustrates a clear imbalance. Some flags are under-tested, while others are over-tested. There is another example of write sizes. The x1 axis shows the log-base 2 of the write size. The x2 axis shows the actual size as corresponding to the x1 axis. The y-axis uses a log-base 10 scale, which shows how many times each write size was exercised by the testing tool. Similarly, many write sizes, especially these larger ones, were missed by most testing tools. This gave us a useful insight. By targeting those missed inputs, we can improve both the input coverage and the test effectiveness. We evaluated the bug detection ability of CML curve compared with the original Crash Monkey. We ran the same test workloads on both tools and look at the exclusive test failures. So these are like failed tests that reveal the bug detected by only one tool, either CML curve or the original Crash Monkey, but not both. This measure captures each tool's unique bug finding capacity. Note that a single bug can trigger multiple failing tests. On kernel 5.6 out of 426K, workloads, CML Club uncovered 400 exclusive failures, while CrashMonkey found only 31. On kernel version 6.12, with about 379K workloads, CML Club still finds more, with 322 exclusive failures compared to 115 from CrashMonkey. Overall, CML Club consistently reveals significantly more unique bugs than CrashMonkey. At the bottom of this slide are examples of bugs uniquely detected by CML Club. This underlying system calls highlight the inputs that our approach improves. Let me wrap up with our conclusions. First, we find code coverage by itself is not strongly correlated with effectiveness in file system testing. Second, effective testing requires more than code coverage. We also need to measure input and output coverage to capture what tests are really exercising. That's where our tool, IOCOV, comes in. It measures input output coverage to highlight both under-testing cases and over-testing cases. It provides actionable insights to improve testing. Finally, we extended this with CML Curve, which improves input coverage in existing testing and enable us to detect more crash consistency bugs in file systems. That concludes my presentation. Our work is open sourced, so I encourage you to explore it. You can also find more details in the paper. I'm happy to answer any questions.